All right, so this is, I believe, the second in a series of new material lesson sets. I think it's lesson 26, but I'll have to check. Regardless, what we call it, it's practice. And practice is how you get better at math. So let's do some practicing. I put parentheses around. I didn't have to, but I did. Got some parentheses, which we'll show in a little bit. So this particular type of graph is in graphing form right now. Everything you need is at our fingertips. So what are the important values that I see? Well, I see the y-intercept. If I get a 0, I'm -6/5. That's a given. I can see what makes the numerator 0, -2. We talked about that in the last lesson set. So that's going to be an x-intercept. And it's undefined at x equals 5. Going to get some asymptotic behavior there. And I can see the end behavior is y equals 3. Y equals 3. Then therefore, I have the graph. And we'll analyze this in more detail when we look at the limits. Okay, it doesn't hurt to throw some numbers in. Let's pick a number bigger than 5. How about we do 7? We should get an answer bigger than 3. 21 plus 6 is 27. I want to make sure I'm doing that. 21 plus 6, 27. And 7 minus 5 is 2. So at 7, we should be getting a value of, this is not drawn to scale very well. 7 gets me, 7 gets me what? 13.5. So I got to redo this now that I put that in there. It's doing that. And so 7 gets me 13.5. All right, and that gives us some feeling for we're headed towards positive infinity. We're headed towards negative infinity, and let's analyze that in more detail by using some numbers. So how did I know that that was heading towards 3? How did I know 3x plus 6 over x minus 5? Because when we start putting big numbers in, these don't matter. Those numbers, only the biggest players in the quotient are going to determine end behavior. And I think we can see that's dividing out, which gets me 3 divided by 1, which is 3. That's how I knew that. But let's actually put some more numbers in and see how it happens as I head towards infinity. Let's just start with the number 10. 10 gets me 36 divided by 5. 36, why did I write that? 36 divided by 5. How about 100? 100 gets me 306 divided by 95. How about 1,000? 1,000 gets me 3,006 divided by 995. Now let's approximate. 995 is pretty close to 1,000, and 3,006 is pretty close to 3,000. So that's what this is, approximately 3. And that's why I immediately saw that over here in behavior by putting in numbers and seeing what happens. Now, what happens when we want to go 5 to the right? Well, I've started that right now. 5 to the right means that we already know that 10 got us 36/5. Let's go to 8. 30 divided by 3, which is 10. That is equal to what? 7 times 5, 7.2. Now I've got 10. How about we go to 6? 18 plus 6, 24 divided by 1, that's 24. How about we go to 5.5? 5.5 gets me 15.5, 21.5 divided by 1/2. 21.5 divided by 1/2, which is doubling that, which is 43. These are values that I'm getting. So as I'm heading towards 5.01, that's what heading to 5 from the above, pick numbers that are bigger than 5 and move towards 5. I think we can see it's infinity, and certainly the graph bears that out. All right, so what happens when I go in from the other direction? I get a sign change, right? When we look at this, let's cut to the chase. Let's put 4.5 in. Let's put 4.5 in, and then 4.9 and then 4.99. I may avoid those right now because I don't want to get caught up in too much computation. But let's look at 4.5. 4.5 minus 5 is minus a half. And 4.5 times 3 is 12, 13.5, 19.5. Well, I hope you can see that we're beginning to double these values when we pick that number, but they're negative. And what happened over here? The closer I get to 5, intuitively, I hope you can see negative infinity. Right, René Descartes serving a good function right now, going back and forth. So what is the limit as x goes to 5? Now, this is the first time you've heard this, or maybe the second. I think I might have said it in the preview of coming attractions or lesson 25. But as I head to 5, from the right, I'm going to positive infinity. From the left, I'm going to negative infinity. And I don't like being at two places at the same time, two different places at the same time. And I'm pretty close to the same moment in time, and I'm in two very different locations. So what's the limit? We say it doesn't exist. Now, if I had been going to positive infinity from the left and the right, then we'd say we're going to positive infinity, but that's not the case. I'm going in different directions, so the limit does not exist. Now, when is f of x greater than 0? Well, let's do a sign chart first. It's easier to look at the graph. I can see when I'm greater than 0 right here. Let's go back to the graph, but then we'll do it with a sign chart. All of these y values are positive. And then as soon as I get to -2 and I move to the right, they're negative. And then they're positive again. These are y values. And that's what this graph is. It's about y values. And I want to know when this function is greater than 0, then I'm really saying when are the y values greater than 0? Well, that determines, that makes us talk about the x values, the inputs. So what inputs get us positives? Well, over here, inputs bigger than 5. So I'll use interval notation, 5 to infinity, right? But there's also another interval over here, which is negative infinity to -2. Negative infinity to -2. And we don't have to learn that on the spot. If you're picking it up already, great. If not, put a smile on your face. We got 2 more lesson sets coming, one tomorrow, one the next day. And I'm a big fan of seeing something 4 times in a row. Consecutive days are great. So let's break this thing up into 2 parts, 3x plus 6. Let's do the sign chart. What's the critical number for 3x plus 6? It appears to be -2. What happens if I got numbers bigger than -2? Positives. All the way to positive infinity. How about the other side of things? Negatives. All the way to negative infinity. Now we also have x minus 5. Let's look at x minus 5. Well, that appears to be positive when x's are bigger than 5, and negative when x's are less than 5. Now remember, if I want to be bigger than 0, I have to have 2 things happening. I either have to have a positive divided by a positive or a negative divided by a negative, and then that quotient will be bigger than 0. Okay, so let's look at the positives. Boom, 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 boom. They're both positive when x's are bigger than 5. Or, looking in the other direction, they're both negative. They're both negative when x's are less than -2. Okay, great. Now, what happens if I also wanted to have or equal to? Well, this equals 0 when x is -2. That's true. When x is -2, I get true. But when x is 5, I get false. Why? 5 minus 5 is undefined. So, greater than 5 or less than or equal to -2, but it's much easier to write the following. Negative infinity to -2, and -2 works. Union 5 to infinity, and that's called interval notation. Because these things are intervals. That's an interval for x bigger than 5. That's the next interval for x bigger than 5. They're both positive. True. Greater than 0. It's the second day you've thought about that. Hopefully it means a little bit more to you than it did the day before. Now we're going to do some unit circle work. The sign of 11 pi over 6. Gosh darn it, I was going to find these values for you, and I didn't. All right, so 11 times 3.14. I'll do it the next time. So that's around 0.52 times 10, 5.2 plus another 5.52, 5.72. So that's roughly 5.72 radius lengths. And remember what a radius length is. Doesn't matter the size of the circle. If that's 1 unit, then 1 unit, I'll do a squiggly line. We start from here, we walk around the circumference, that distance, and that's 1 unit. 2 units is over here somewhere, probably there, probably a little higher. 3 units is here, and 3.14 is right about there. So 1.57 is half of 3.4, and that's 90 degrees. So this would probably be around there. I'm guessing that's close to 2 radian lengths. So 3 times that, 1, 2, 3 times that ends in a 1. 3 times 5, 15, carry the 2. 4.71. So we're looking somewhere over here at 5.72 radius lengths, somewhere in this vicinity. We're going to draw our triangle. Actually, it's a little further, isn't it? 5.72. That's pretty close to 6.28. So 5 points probably in here somewhere. All right, just playing with radius lengths. Now, the nice thing about this is we can get an exact answer. This would be approximating that. Okay, and we'll play with it some more in the other ones. So I see pi in the intro to the unit circle. I hope you know to draw the top half of the circle, break it up into 6 parts. Good drawings get good answers. So here's my 6 parts. There's 1 pi over 6. There's 2, which we would call pi over 3, so on and so forth. 3 pi over 6, pi over 2, 4 pi over 6, 2 pi over 3, 5 pi over 6 right here, 6 pi over 6 right here. All right, a lot of those can be reduced. So now we got 12. 1, 2, 3, 4. I butchered this thing. All right. So what I would do is I know there's 6 here. There's 6 here. So I know I'm looking at something like that from experience. That's a 30-degree angle. And what did we say the ratios of 30 degrees were? 1/2, √3/2, and 1. Well, which side looks to be the smallest? This one here. And that's -1/2. That's 1. √3/2. I asked you to memorize that as a decimal. Does it look like that might be about 0.87 units? The radius is 1. I hope it does. All right, so this answer was -1/2. And we want to be able to, by May 15th, not have to draw it, have the drawing be in our mind's eye, picturing where it is, and simply saying the answer -1/2 in 5 seconds or less. Most people get there. May not feel like you're going to get there at this moment because you're just learning it. Most people can tie their shoes now without having to go through the motions of looking at their notes. Okay, I'm sure your parents asked you to take notes when you learned how to tie your shoe, because that's how you get best recall, opening it up and yeah. Okay, that's another conversation. Cosine of -pi/6. -3.14 divided by 6 is -0.52. Oh, I think I said that number a little while ago. Yeah, I got a feeling it's exactly the same place, except we're going in this direction. Yeah, so let's call this -1. Halfway is right here. That should be a pretty darn good 30, 60, 90. Reference angle 30 degrees. And we just did those values. And I think the cosine is the adjacent divided by the hypotenuse. Now, what was the angle in degrees? 330 degrees. Ooh, gets me a triangle on the circumference of the circle. Boop, 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 right there. I'm going backwards, a half a radius length. Made a 90 degree. My answer with 3/2. What's the cosine look like? Max to max, which means if I go backwards, right? If I go backwards, there's going backwards 30 degrees. Okay, and there's a height of 1 or width of 1, maximum width of 1. And I'm saying you're about 0.87. Makes sense to me. Tangent of 11 pi over 4. 11 pi over 4. Well, let's do 12 pi over 4. 12 pi over 4 is 3 pi. Might as well start to work with radians. Here's pi over 4. Looks like there's 8 pi over 4 to get once around from 0. 1, 2, 3, 4, 5, 6, 7, 8. I want to get to 11 pi over 4. 1, 2, 3. I think I'm there. And I think 180 divided by 4 is a 45-degree reference angle. So that's 45 degrees. And we might as well put that one on the board right now, 45 degrees. 1. That means these are the same. If they're the same, then they got to produce the same square areas that add up to 1. I think we're looking at a half and a half to add up to 1. Okay, so it looks like x is the square root of a half. X is the square root of a half. Oh, okay, well, let's play with that. The square root of a half is the square root of 1 over the square root of 2, which is 1 over root 2, which is 1 over root 2 rationalized, root 2 over 2, which is root 2 over 2, and I've asked you to memorize that. It's about 0.71 as a distance. So this one here is positive 0.71. This one is negative 0.71. And tangent is opposite divided by adjacent. I think this answer is -1. Now remember, this is the second lesson set. No one is asking you to have this down pat. We've got till May 15th, which means that you may just be at the learning stage of following. Following means just watch. No pressure, no expectations, just watch. The second step, maybe on lesson set 4 or 5, do it yourself. Pause the video. You go ahead and do it. And then in class, the third stage of learning, when I see you start explaining it to someone else. Thank you, Sam Richardson. I heard Sam talk about, oops, not maybe giving names out here, but colleague. And I'm really grateful that I heard him say that, and I'm borrowing it. A lot of times that's what folks do. Teachers borrow what they hear. That sounds good. I'm going to see if that seems a little cloudy, the camera, but maybe it's fine. I hope it is. So that was our unit circle work for the moment. Now we'll tend to, let's go to some cubics. Point of inflection. Well, you've already had that. So we want C of positive 6 over 3 C of 2. C stands for cubics. Thought that was pretty sharp. Yeah. All right. And so what did I just do? That should sound familiar. Minus B over 3A, the average of the roots. And if I put that in, I see 8. My next number better be minus 24 because there's supposed to be a minus 3 to 1 ratio occurring. Yep, 24 times, yes, oh, I'm good. Minus 4 plus 5. Well, that's not too bad. I only have to double that and change the sign. Minus 16 plus 1 looks like minus 15. So 2 gets us minus 15. Ah, that's great. Yeah. I can almost start to put this in graphing form. X minus 2 cubed, X minus 2 minus 15, and the A term is 1. I don't have to write it, but I will. 1. There it is. 1. The only thing I'm missing is the rate of change at the point of inflection, and then I've got this written in graphing form, which means I'll be able to see what it looks like. And the rate of change at the point of inflection comes from c minus 3ah squared. I'll eventually explain to you how I got that. I got that before I started teaching calculus, so I didn't use calculus. C, in this case, is minus 2. All right, A, B, C, D. All right, in a linear function, we only have A and B. In a quadratic, we have A, B, C. In a cubic, we have A, B, C, D. All right, where was I? Minus 3. A was 1. What's H? Well, we're going to find out that H was the X value at the point of inflection, and we're going to be going down at that rate fastest. That's where we're going down fastest, and we'll explore that later. We'll get into this more deeply as we go along, but we found that H was 2, and that's get squared. So at the rate of change at the point of inflection is minus 2, minus 12, minus 14. All right, so we're getting ready to graph this now. I'm going to make some space. The final frontier. Yeah. These are the void. Oh, no. It's a math class. I forgot. All right, so I'm going to draw a y-axis. I'm going to start at 0, 5. Let's call that 0, 5. I'm going down at 2 to 1. 2 to 1. Okay, so let's put the 0, 5 above it. 2 to 1, but at the point of inflection, I'm going down at 14 to 1. And then I'm coming back up. And 2 to 1 means I'm not, pretty soon I'm going to have an X value here that is close to 0 for my local max, and one over here a little bit further to the right for my local min. How do you find those? Intercepts, asymptotic equation. There's no asymptotes in this. Well, no, there are no asymptotes. Rate of change, x-intercepts. We're not going to actually find the x-intercepts. We're going to find the max, local max, and local min x values. All right, so how do you do that? Well, let's put it in graphing form here. So c of x equals 1 times x minus 2 cubed minus 14 times x minus 2 minus 15, I believe, is what minus 14. I already forgot what that was. Minus 14. No, that was the rate of change. Point of inflection was minus 15, I believe. All right, so let me do it again. 2, 8, minus 16, minus 4, minus 20, plus 5, minus 15. Okay, I'm good. All right, so now what is this x value here? Let's put it there. Not hard. It starts from measuring from 2. So we got 2, we got a plus minus, but in this case, just the minus, because we're looking in this direction from 2. This is going to be 2 plus. And it turns out it's the square root of, I got to put this down here. The rates of change dictate this. So positive 14, it's the opposite of the rate of change at the point of inflection divided by 3 times A. And what is A? A was 1. There you have it. And this one is 2 plus the square root of 14 over 3. That's not tough. 14 over 3 is, a little bit more than 4. So a little bit more than 4 units to the right would get us my local min, and a little bit more than 4 units to the left would get the x value of the local max. Quick and easy. All right. And again, just trying to put some things in your head. Day 2, maybe a little bit further along than day 1. Day 4, magic happens. Direct variation, y equals k over x is what we talked about. Yes, not k times x, excuse me. That's direct variation. We drop the 5 in. We drop the 10 in. Looks like k is 2. The constant of proportionality is 2. So if all of a sudden I say x is 6, I think we can figure out what y is. Inverse, what I accidentally started doing the last time. K over x. 5 gets you 10. Okay, so looks like the constant of proportionality is 10. Is 50, excuse me. All right, and if I'm going to switch my x's and my y's, and I just did, I turned 5 into 10, I got a feeling y's got to be 5 intuitively. All right, but let's actually throw our new x in, 10. Oh, geez, that formula seems to work. Yep, I inverted the x's and the y's. But I don't also want to do that too often because inverse means really as one number goes up, the other number comes down. All right, direct, they both go up. All right, so I could be sending you on a goose chase there by that language that I just used, but in this case, it was an inverse. Jointly, so y varies, constant in proportionality. Y varies jointly as x cubed and inversely as the square of z. And we're just going to practice how to write joint variation. And then we throw 3 variables your way. You can find k, give you another 2 of them. You can find the missing one. All right, ln of 12/5. What is that? A lot of people are starting to get these. And so 12 is, let's see, 1.4 plus 2.5, 2.5 minus 1.6. 2.5 minus 1.6. So it's approximately equal to, what, 0.9? That's what I believe I'm getting. But I don't trust my mental math much anymore when I'm talking to you, based on how the history of how I've done recently. Cognitive decline continues. So 12/5, let's do it organically. And then we'll express our answer as the sum and difference of logs, which is getting at the rules of logs, which is the rules of exponents, really. All right, so 12/5, let's look at that in E notation. First off, let's break it down to 2 squared times 3 is 12. And 5 is, well, it's just 5. Okay, so 2 squared is e to the 0.7 squared, roughly, times e to the 1.1. And that's over e to the 1.6. These are all approximations for 2, 3, and 5. So what do I have? 2 times 0.7, which is 2 times the ln of 2. 0.7 is the ln of 2. Plus 1.1 is the ln of 3. Minus 1.6 is the ln of 5. Okay. This multiplication is really, let's write that, ln of 2. I'm really multiplying 2 times the ln of 2, and that could also be written as the ln of 4. Okay, so this could have been the ln of 4. We'll change it again in a minute. And when I add exponents, there's an implication of a multiplication of quantities. So there's your 12. There's your ln of 12 right there. And subtraction implies division. And back to ln of 2 times 2. ln of 2 squared. Okay, I should put that in brackets now. Order of operations, right? And this is in parentheses right there. So 2 squared is 4, but I'm expressing 2 as e to the 0.7, which means I'm really breaking this up into ln of 12 minus ln of 5. There's the division. ln of 4 plus ln of 3 minus ln of 5. Sums and differences of logs. 4 could have been 2 squared. Put a bracket around that. And then I get 2 ln of 2 plus ln of 3 minus ln of 5. And why is it useful to do that? Become an astronomer and you'll know. If you're working with huge numbers, if you can just work with the exponents, and then when you're all done, put it on top of the base, and it shortcuts all that huge computation. So this was a major breakthrough back in the 1600s by a guy named Napier. And then a lot of things changed. People like Kepler, Enlightenment period, studying the stars. All right, sketch. Well, what do I see? You see this thing goes to 0 immediately. I see that -6/5 is the y-intercept. 0 gets me -6/5. I see that there is no x-intercept. Nope. Never crossing, nope. Never crossing, just not going to cross the x-axis. But I know it goes to 0 here as well. How do I know that? Because I've put numbers into the equation. Where is this asymptotic behavior? Over here on the right. What do we get on the right? Big numbers. Let's put 100 in here. 6/95. You tell me on the number line, 0, 1. Which one is it closer to? Let's put 1,000 in. 995. I think I'm even closer to 0 than I was before. So I want to put 1,000,000 in here. 6 millionths. Pretty small number, but it's positive. That much I can see, it's positive. So I know I'm undefined again at 5. I picked that for a reason, hoping that you spotted it. X equals 5. Let's throw a number in here like 7 again. 6. 6 minus 5 is 1. 6 gets us 1. So let's call this 6, 1. All right, so I know I'm doing that. I get a sign change here, because as soon as I pick a number less than 5, I get a negative going to 0. There we have it. So what's the limit of f of x as x goes to infinity? 0. What's the limit of f of x as x goes from 5 to the right? Positive infinity. What's happening if we come in from the left? Like 4.9999999. Sign change. So that's going to go to negative infinity. When it was a positive, I'm not sure what I wrote over here, but it should go to positive infinity. What happens when I just go to 5? Same thing in the last problem. Heading in different directions. Does not exist. And when is this thing positive? Well, 6 is always positive. So it's positive when I get a positive. That only happens one time when x is greater than 5. I think all these y values here are negative. I think all these y values are positive. When do I get a positive? When I pick x's that are over here. Bigger than 5. All right. So that's that one. Mixture problem. I have a candy maker now. Like I know anything about it. I don't. And I do know something about mixtures now. I want 40 pounds at 80 cents. 40 pounds at 80 cents. Okay. From what? 60-cent batch and $1 batch. And I made this up so that we hopefully can see that 90 cents probably going to be the magic number. So 40 pounds at 80 cents. So I got 40 cents, 40 pounds, 80 cents. So there's my cents. Okay. So here's our 40 pounds. That's our total. And I'm breaking it up into some smaller parts. Oh, I took something away. Then I think this is 40 minus whatever I took away as it did. Okay, I hope that makes some sense. So I want 60 cents at some price. Then the other price has to be the $1, 100 cents. 40 minus whatever I'm using at the 60-cent mark. So that's 60x plus 4 with 3 zeros. 1, 2, 3 minus 100x. So that's going to be equal to 32 with a couple of zeros. Let's throw our x's, minus 40x to the other side. Let's make it positive 40x, putting these together, moving it over there. Let's take that away, which is 800. Sure looks like I've got 20 pounds. Yep, 40 into 800, 20 pounds. So I split it up evenly. So I said something wrong about 90 before, but here's our symmetry. So 60 at 20, 20 at 100, right? It's going to give me 80. So I don't know why I was saying 90 before, just cognitive decline continues. All right, there's our mixture problem for the day. Now we're going to do our one derivative. We're going to look at the point, the vertex using a derivative. And so we'll talk one more time about the geometry of squaring. So here I have 3 squared, gets me 9 units of area. if I make my dimension 0.001, which is kind of a small change in x, why don't we call it a difference of x's? But keep in mind, it's really small. My area just got bigger. I can't even show it. It's really just a slice, a new layer of area. You know, how much new area did I get? Well, we could call that dy, a change in y. All right, and I can see it over here, 0.0060001, which is another way of saying 0.0006 plus 0.1234567 And that is this amount here at the cusp. And we are definitely going to ignore that. If Nassau can ignore past 8 decimal places, we can in class 2. So I really have a change of 0.006. And my new dimension, my change in x's was 3 to 3.001, a change of 0.0001. Sure looks like a 6-to-1 rate of change, which happens to be twice the x value. And we looked at that in the last video. That seemed to be true for every x value at x squared. Now, what happens if I double this? Then 9 becomes 18, 9.006 becomes 18.0012, and instead of 6-to-1, I get 12-to-1 units of change. Now, what do we know about this from our previous study? We know it's cup shape up. We notice minus p over 2a gets us the x value. 20 divided by 4 is 5. Well, if I look at rates of change, the change of y, which is q of x, divided by that little dimensional change, right? Looks like it's 12-to-1, which comes from, in this case, well, that's just one instant. So the rate of change of x squared is 2x, and I'm doubling it. That's what I tried to show here. And the rate of change of a linear function is minus 20, right? It's just the slope. And I know something about the rate of change at that x value is slope is 0. And we looked at this in the last lesson set, right? And I've got a handout that I gave you. I think I gave it to you, but I'll make sure. And I'll put that handout, I'm going to put it on a whiteboard for tomorrow's lesson set. Remember, you're just following at this stage. But what can I do? I can say that this is, let's call this y. In math, sometimes we call this y prime. And y prime is equal to 4x minus 20, just coincidentally, that slope is 0 at what x value? When is 4x minus 20 equals 0? Oh, what a coincidence, at 5. And I've been saying you're going down at 20-to-1 at the y-intercept. So I know my y-intercept over here, 0, 7, is going down at 20-to-1 at that instant. How do I know that? Because I can look at the rate of change at 0, and I get 4 times 0 minus 20. Oh, it's going down at 20-to-1. Now, that's not how I did it originally for you over the course of the first half of the semester. Over the course of the first half of the semester, we did it from the standpoint of plug a 0 in, 0, 0, 7, plug 0.001 in, gets you 0.002, multiply by negative 20, gets you minus 0.020, and that hasn't changed. That hasn't changed appreciably. The change is negative 0.020, and if I divide that by 0.001, I get a feel for going down at 20-to-1 at the y-intercept. All right, so that gets us going. Again, you're still in the follow stage. Tomorrow's lesson set, hopefully you pause the video, try it yourself, see how far you can get on each topic. And then the next lesson set after that, we do it again. And if you're doing all 4 lesson sets, and I just found out I can look online to see how much homework you're doing. Boy, I wish I knew that earlier. So we're going to have a few conversations when some people get back. But for now, we're in good stead. All right. Yasser, if I made a mistake, please post it. Appreciate it, because I'm off running around for the next 12 hours. Stay safe and warm.